So now we're going to talk about how gradient descent works on quadratic functions. So we'll talk about how steepest descent works on the class of functions that are all quadratic. So a nice, very ubiquitous set of functions. So here's what quadratic functions look like, and actually, the form that's on the left here is not quite as useful as the form that's on the right. So you can factorize, you can refactorize the form on the left into something that's centered on the minimizer there, which is going to be at x equals p. And so the steepest descent algorithm looks like this. So you plug in xk plus lambda uk, and what's my descent direction uk is the negative gradient of the function. So what we want to do here is we actually want to write out what steepest descent actually looks like on a quadratic function. So the first thing, so what we're going to do is gk as a function of lambda is going to be this quadratic function xk plus lambda uk. And really what I want to do, well, let me write out where uk is going to be the negative gradient of qk, evaluated at xk, and that turns out to be equal to negative a xk minus p. So if I use the form of the quadratic function that's centered on the minimizer p, then the descent direction turns out to be that expression there, which is useful to us. So this is the direction that I'm going to step in, uk, and really I want to choose lambda here such that this is such that I minimize this function as much as I can. So in the direction that I'm going to walk, I want to take the best step downhill that I can and end up at the minimum in that direction. So I want to figure out what the minimum of this function is with respect to lambda. So really what I want to do here is I want to differentiate this expression with respect to lambda. And so differentiating this, I'm going to need to do the chain rule on this thing. And so I'm going to get the gradient of q xk plus lambda uk. Right, so differentiating the inside here with respect to lambda, I get a uk. It has to have a transpose in it so that all the dimensions work out. Now I know what the gradient of q is. So the gradient of q is negative of that. So this is uk transpose a xk plus lambda uk take away p. Right, that's my expression there. So I can expand this out here. So let's expand this out. So I'm going to get I'll expand out this term first because it looks interesting. Right, so you can see I've got a uk transpose and a uk. So let's collect those together, and then I'll glomp everything together. So the other stuff is going to be uk transpose a xk minus b. Right, so I pulled that term out because it looks interesting. And actually, the thing that's left here, well, a times xk minus p, that's equal to negative uk. So let's not touch that first thing, term there. And this turns out to be uk transpose times uk. So that's the derivative of this function with respect to lambda. I want this to be equal to 0. Right, for the minimizer. And then I want to figure out what lambda makes. I want to solve this equation here for lambda, and that's pretty easy to do. This is, I'm just going to pull this over to the other side. So lambda is going to be equal to, let's call it lambda k, because it's going to depend on what k is. This is going to be that term divided by this, uk transpose a uk. So why is So this gives me the sum of squares of all of the terms in UK. So it's the dot product of UK with itself, which is the norm of UK squared. So that's my lambda k. That is how far I want to step in my descent direction u. And of course, the nice thing is, if A is positive definite, right? So if A is a positive definite matrix, then it means that that denominator there is not equal to 0. In fact, it's positive. So this never blows up. So the positive definiteness actually makes a big difference there. So now that we've done that, let's figure out what qk plus 1 is. Or q of xk plus 1. Right, so that's going to be equal to q of xk plus lambda k uk. So I'm going to plug this in to the expression for a quadratic. That looks kind of messy, so I'll just write it out and then we'll talk about it. So xk plus 1 minus p plus d. Right, so that's this nice factored form. So what's xk plus 1 here? Xk plus 1 is that expression. So in fact, this is going to become even messier. Xk plus lambda uk take away p, transpose a, and then the same thing again, xk plus uk squared, uk minus p, I think I'm just on the board there, but that term is divided by uk transpose a uk. So that's a fairly ugly expression that you can expand out, and I will expand that out in this way. So the thing that you can see here is that there's a plus d here. I can collect up the xk minus p transpose a times an xk minus p transpose plus the d, and that's actually going to give me q of xk, right? And then I just have to write out all of the remaining junk that comes from this term multiplied across. So let's write that out. So half lambda k, I ended up getting a lambda k squared, uk transpose a uk, and then I end up getting lambda uk all squared. Yes, is what comes out there. So it looks, it all looks quite messy. And now, what this turns out to expand out. If I actually plug in lambda k into this expression here, then I get something that looks quite nice. Okay, squared. And that is because that comes from the definition of lambda. So that is because in this second term here, that's the negative of that. So lambda k uk transpose times a times uk is equal to uk, norm of uk squared. And so that term I can replace with lambda k uk squared. So what's the point of this? That term's always positive, right? So this is always less than lambda xk. Q of lambda xk. So in other words, the thing that we prove here from doing this is that when I apply steepest descent to a quadratic function, I'm always guaranteed to be heading. I'm always guaranteed to be heading downhill. So this will actually work. It will converge to something. Okay, so doing an example. So let's think about an example that works quite nicely here. So a quadratic, the two-dimensional version of the quadratic y equals x squared. So that's symmetric about the z-axis. If you differentiate that function, so right to get our descent direction. So if I calculate by hand the first step of this, I need to differentiate my function. So you differentiate the x1, you get 2x1. You differentiate with respect to x2, you get 2x2. So the gradient is that, and my first descent direction is going to be negative of 2x0. I can calculate lambda from the analysis that I just did, from the expressions that I just derived. So plug u0 into the formula for lambda that I just derived on the board, and I get a half. So it turns out that x1, my second step is x0 take away x0 equals 0, and that's the minimizer of this. So actually, in this nicely behaved quadratic function, a thing that looks pretty much like exactly y equals x squared, I'm guaranteed to converge in just one step, and that's no matter where I started from. So that's entirely because this is a perfectly symmetric quadratic function here. So when I'm symmetric and I have steepest descent on a quadratic function, then I'm always going to converge. And you can see that if you think about what this looks like, right? If you think about what this function looks like from above, right? This quadratic function, what do level curves of this look like? They look like circles. Right? So if I start anywhere here and I head downhill, if I think about a tangent line to any of these level curves, where do I point when I head downhill? I always point, no matter where I start, directly into the center. So on any of these level curves, they all point straight into the center. Right? And so I'm always going to, if I take the best step that I can, I'm always going to hit the bullseye. I'm always going to head right to the minimum in one step. So that's beautiful. That works well. Here's the example that I looked at before, the slow to converge one. Having my formulas now, I can actually figure out, I can actually show that if I start at, say, the point 5, 1 here, then this is what the sequence of iterates here looks like. So I can actually calculate exactly what those steps are. So that's a nice example to do. It doesn't take too long to do, and that's a good example to look at. So it converges, but you can see that it converges slowly because of how the problem's set up. And that's it.